current nuclear technology is, actually it's not unsafe, but it's a fundamentally dangerous process that has to be wrapped around with a lot of containment systems to make it safe, and those systems are incredibly expensive. So it's safe, but unaffordable, which is a challenge for the world, because we need a carbon-free source of electricity that's not just wind and solar. Those things are brilliant, but will not meet global demand on their own. So we need something else. And current nuclear isn't it, because it's too expensive. And so the only alternatives at the moment are coal and gas. And those power plants are still being built. Right now there are over 1,000 fossil fuel power plants being built around the world, or planned to be built around the world. And if we do that, we will totally fail to get anywhere near making an impact on climate change, right? The thing is, though, there's an alternative nuclear technology, right? And it was developed in the 60s in the US. They're called Molten Salt Reactors. One was built in the late 60s in the States and operated for several years very effectively. The technology wasn't developed at the time. Two main reasons. One is it doesn't produce weapons-grade plutonium as a byproduct, and so governments weren't very interested. I mean, you know, governments supported their nuclear industries then for weapons, not for electricity. And at the time, pressurized water reactors, ordinary current nuclear technology, was actually relatively cheap. I mean, it was relatively cheap because they actually weren't really safe enough. And 3 Mile Island was perhaps the first time at which the additional systems started being put into that technology and made it more and more expensive over time. So, existing technology called molten salt reactors, two crucial differences between those and current nuclear. One is the reaction takes place at atmospheric pressure. So it can't blow up. There's no contained pressure to blow up. And the radioactive gases that are produced in ordinary nuclear power stations are not produced by molten salt reactors. They don't exist. And so you can't have an explosive release of gas. There's no gas, there's no explosion. Right? And then the second thing is that as the temperature rises, the reaction slows down. So the thing can't melt down. It gets to a certain temperature and then just stops there. And so because there's no meltdown, there's no explosion, the engineering of the system is very, very much simpler and therefore cheaper. And so our plant would be about 1/20th of the size of a current nuclear plant with the same power output. And there's a therefore massively cheaper. So we reckon we can build these plants for not just less than the cost of nuclear, we can build them for less than the cost of coal or gas. And that's the crucial thing that you have to be able to do. The design used in the US, that lots of molten salt, there are other molten salt reactor companies apart from us. They're mostly following the same path though, which is to take that and replicate that design. It takes a radioactive molten salt and pumps it around the system. And radioactive molten salts are highly corrosive. And if you're going to pump it around a system, and the system needs to survive for 60 years, which is the life of the plant, then there's some very significant engineering challenges in fighting corrosion in those environments, in alloys and so forth. So difficult. We've addressed that problem by not pumping the radioactive salt around, by keeping it completely stable in a fuel cell actually, and having a separate salt which provides the cooling. So that, at a stroke, removes the main engineering challenge. And it seems like a relatively simple idea, but then I think all good ideas seem relatively simple afterwards, right? In the world of renewable energy, wind and solar are unpredictable. And so it may be a windy day, it may be a sunny day, it may not. But demand is predictable, and demand varies over the course of the seasons and over the course of a day. And so every grid system needs a variable power source. At the moment, the only variable power source is gas. And so that's how that's how grids work today. We have a system that sits alongside our reactor that allows us to store the energy and release it to the grid when it's needed. So we can produce a variable output from a nuclear power station. Nuclear is a steady, producing system. Right? In a 1 gigawatt plant, we produce 1 gigawatt hour every hour. What we can do is to store that energy, release it to the grid when it's needed, so we can peak. Which means that it's possible then to have a grid which is made up entirely of carbon-free sources. And that, I think, is probably going to be quite important in the future. Yeah, so we've got there's an organisation, New Brunswick Power, who want to build one. If everything goes to plan, we'd expect that reactor to be operational by 2028. So less than 10 years from now, which sounds like a long time, but is not a long time, as you know, in this field. We have a lot of interest from nuclear engineering companies, and the fact is, those businesses who build power stations for a living face an uncertain future with current nuclear. There are two major projects in the UK which have both just failed. Toshiba and Hitachi have pulled out of new nuclear power station builds, and so we're getting close attention from nuclear construction businesses, engineering businesses, consultancies, from governments, and no, we're very positive about all that. Prediction's probably the wrong word, right?
Okay.
The fact is that generating electricity from fossil fuels is the world's biggest source of carbon emissions. And to do anything about that, one has to roll out an alternative on a very large scale. So building one or two of these plants, might be interesting, but it's not going to solve the world's problems. I mean, not by a long way. And so we're scaling the business so that it's capable of supporting that kind of scale of rollout. And we're doing that by being the people who just design the reactors, not the people who build them. We want lots of people to build them. The more the better. We'll design and license those designs, and that's our contribution. And then, it's possible then for them to be being built simultaneously all over the world. And it's only if we get hundreds of these things that will actually have made an impact. And, frankly, that's what we're trying to do.